Welcome back. This is lecture 19 of our lecture series, and now we have been looking at quantization for fermion fields, right? We have been looking at, last lecture we looked at how to canonically quantize the field that is present in the Dirac equation. What we want to do today is take a look at how you would go about making a path integral for those fields, right? So I listed here the main references where you see this path integral done for fermions, right? And today we're following basically what's doing on the second half of section 12 of Anastasis. And the main question we have to be careful about is that now we know that if you calculate observables with path integrals, right, you'll be doing the path integration over fields, right, weighted by the action, right? This is in the Minkowski space, should be a minus s for the Euclidean space, but then you have something here, right, or even two fields here, which are now functions, right? These are functions, and this is for a bosonic theory, right? And since they are functions now, they commute, and it doesn't matter because we know that this path integral will give me the time order product of these seen as operators, right? This is the same as the time order product of phi1, phi of x1 and phi of x2. The states here depend on the conditions on the integral, and we know all that story, right? But the point now is how do we implement that for fermions, right? Because we know that there is some anti-commutation relations between fermions, and we want this to carry over to the path integral formalism, right? Another way of seeing this is that you know that these functions, these fields, can be written as operators as combinations of A and A daggers, right? And the way to make these into a function, to make these into instead of an operator, a function, would be to remove the commutation relation for these guys. One way of thinking about this is to think that these, if we have been using natural units, but if we didn't, the commutation relation between these two guys is proportional to h bar, right? And we know that if you take h bar to 0, this commutator goes to 0, these guys become commuting numbers, and this operator becomes a function, which is what is here, right? We don't have these guys as operators anymore, right? Using the same kind of logic for the A and A dagger that showed up in the fermionic case, right, which would also be proportional to h bar in the case we have been using, not using natural units, right, would be to have these guys in the limit in which you take h bar to 0, right? In analogy of what we can do here to get functions from this operator, right, would be to have these guys are as anti-commuting numbers, right? And then somehow we'll get to that, build anti-commuting functions here. And these are very special numbers, of course, but luckily for us, they already have been studied in mathematics for a while, right? And this is what we call Grassman numbers, right? So essentially, in order to write these path integrals for fermions, we'll have to deal with numbers that are anti-commuting. So we can basically build an algebra for these Grassman numbers, which is based on anti-commutation relations, right? And this will be true also for these guys, right? I mean, basically, this was already 0 for the operators, will be also 0 for the case where these guys become Grassman numbers. And you can see that it's easy to show that you can also build commuting numbers out of these guys, right? If I make a product of two anti-commuting numbers, I get a commuting number. And we'll take a look at that more carefully. So the mission for today is to build this algebra for the Grasma numbers, right? I won't be at a mathematician level of rigor here. I couldn't even if I wanted, right? But I'll try to just do the minimum necessary for us, and we'll try to apply that to fermionic fields. Okay, so the Grassman algebra will be generated by a set of generators, which I'll call theta I, with I going from 1 to n, right? So that any two of these theta I, take theta I and theta j, right, anti-commute between themselves, right? Of course, that implies immediately that any of these generators square is 0, right? All you have to do is substitute them here, and these and you show that any Grassman of these Grassman generators will be 0 if you take the square of it, right? This n can be a finite number, right? So I can have a finite Grassman algebra, or I can take n to infinity, right? For our that can be a little subtle, but for our uses here, we won't need to do that. So mostly we can assume, you see, we can assume that this n is finite. So we have a finite number of Grassman generators, right? That has a lot of consequences, right? For instance, if I take any three of these generators, theta 1, theta 2, and theta 3, right? And I use these relations, I see that if I commute these two guys, I get theta 1 minus theta 1, theta 3, theta 2, right? And then if I commute again, I have theta 3, theta 1, theta 2, which means that this object here commutes with theta 3, right? That divides my algebra into two parts, essentially. I have even elements of the algebra, right? Or commutative numbers, you see that called C numbers. And this is one element of this even or a C number part of the algebra, right? And I have an odd, sometimes called odd, or sometimes A number, but for anti-commutative number part of the algebra. So you see a product of two A numbers will be a C number. A C number times a number becomes an A number again, because if I put theta 4 here, I show that it anti-commutes with the product of these three, right? So as you multiply more and more A numbers, you alternate between the even and the odd part of the algebra, right? And then I can write in general, right, any number in this algebra as suppose n is only 2, right? So I have only two Grassman numbers. Let's call theta 1 is as theta, and theta 2 I'll call eta, right? Then it's easy to see that I can write any object of this algebra in terms of theta and eta very simply, right? Let's make something similar to a Taylor series here, right? I have some coefficient plus a1 times theta plus a2 times eta, a3 times theta times eta, and now there's nothing else, because if I try to put any extra powers of theta or eta, that will be 0, right? Theta square is 0, eta is 0, unless I have more generators in my algebra. That's all. That's basically anything I can build within this space of two generators here, right? And that's because this property of Grassman numbers make everything really simple to work with once you get used to Grassman numbers. It's actually the series is finite in this case for finite Grassman algebra, and we will use that a lot, right? Also, implicitly here, I'm defining this product and sum within this space, which is satisfies all properties of scalar products and sums in vector spaces that you used to, right? The important thing to notice here, since this is finite and there's no more generators, A0, A1, A2, and A3 cannot depend on theta or eta, otherwise these terms would be zero, right? So they're just complex number in the most general case, right? They are commuting numbers, they are C numbers in the sense that they're not part of the Grassman algebra, but they can also be complex, right? And then you see that the properties of this guy depend on these coefficients, right? So if I make A1 and A2 equal to 0, I'll have only this part and this last one. This guy will become a C number, right? Because this part and this part belong to the even part of the algebra, right? And if I take A1, actually A0 and A3 equal to 0, and these two different from 0, then this will be a number and belong to the odd part of the algebra, right? Because these guys are anti-commuting, and these are just complex numbers that commute with everything. But in general, I can have an object that is not commuting, not completely commuting, nor anti-commuting. This is the most general combination. This is sometimes called the super number, right? And if you look for super numbers around, you see careful study of the properties for this guy. I hope it's clear that this generalizes pretty easily for more generators. So if I go for an algebra that contains 3 of these Grassmans, let me call the third one rho, right? The series is still finite and now looks like this, right? It has every possible combination of theta, eta, and rho, but only to taking any of them to first power, because if you try to take the square of any of these guys, this will be 0. So this is the most general object you can build between the Grassman algebra and the complex numbers, right? Taking the coefficients as complex numbers, right? This is the most general thing, and you can do that for 4 generators, 5. The series will be finite as long as the algebra for Grassman's numbers is finite, right? So that's good as long as we're doing only algebra. But we know that we also want to do calculus, right? We want to define integrals and derivatives for these Grassman numbers in order to do the path integral quantization, right? In the case of the derivative, the extra care we have to take is about the direction, because, you know, these guys are anti-commuting. So let's stay just for simplicity's sake. In this case where my algebra is just, the size of my algebra is just 2, right? I just have theta and eta, right? I can define the derivative in the way you would expect, but I need to define if it's acting from the left or the right. Let's try to the left one. So I put an L here to define the left derivative. If I do that on theta, right, for any object in my algebra, right, this will be just A1 plus A3 eta, because I know I can always write this like that, right? So this is the effect of the derivative. But if I act on the right, I'll define the right derivative in this way. This is the definition, actually. but you can see why this is what you would want, right? Minus A3 eta, right? Because now I have, if I coming from the right, I have to go over this guy to act on theta. So I'm defining this in this way. And consistently, now the left one acting on eta will be just, right, if I look up there, it will be just A2, and now minus A3 theta. So I'm making the derivative itself into Grassman numbers part of the odd part of the algebra. Right? And same for the right one, following the same idea. Will be just A2, and now I don't have to go over this guy. I'm coming from the right. It's just A3 theta, right? You can see that you can go from one derivative to the other pretty simply, and we mostly don't need to use both, right? We can always rewrite derivatives in a way that I'm always acting from the left. So I will define these, right? So when I just write the derivative, it means, right, these are all definitions. It means the left one. So if I ever need to use the right one, I'll put this explicitly. If I leave the symbol hidden, that means I'm using the left one. Now let's look at some properties that are a consequence of this. So if I calculate eta del f del eta, right, this will be this object multiplied by eta, right? So it'll be A2, oops, no, this object multiplied by eta on the left, right? So A2 eta minus A3 eta theta, right? Which I can rewrite as A2 eta plus A3 theta eta. Right? Now, if I do just the product, let's say I just multiply eta by f. Again, I'm using the general expression for f. Right? So if I multiply this expression by eta, this will be 0, this will be 0, and these two end up with eta multiplied here, right? So I get A0 eta plus A1 eta theta. And now, let's differentiate this guy in relation to eta, right? Eta f. This will be just A0 plus A1 theta, right? I'm just differentiating. Notice that the answer is A0 plus A1 theta plus if I add up these two, right? Let's say I take this plus this one, right? This is A0 plus A1 theta plus A2 eta plus A3 theta eta, which is f of theta eta in general, right? This is the general solution. So what I'm showing here is that this plus this one is just f, which allows me to write the product rule for this derivative, right? What I'm seeing here is that del eta of eta f is just f minus eta del f del eta. Right? So when the derivative goes through, so the first term is what you expect from the product rule, but the second term, the derivative has to go over eta and you get a sign. Right? It's not difficult to show that this is very similar for even for bigger Grassman algebras, and you have just derivatives that are really just part of the odd part of the algebra. Right? So eta I will anti-commute with derivatives, delta eta j. Right? This will be just Kronecker delta. And derivatives anti-commute between themselves. So if I take a del eta and a del theta, this will be 0. These are all consequences from the definitions I used above, and you can show them just applying these to the generic function in the space, right? This, as I said, for a most general case, and that's what we use a lot, will look like that. So if I take a big product of Grassman numbers, say theta 1, theta 2, in a bigger algebra, all the way to the theta n of the space, right? This will be equal to delta 1j, right? Eta 2, eta 3, oh, theta 2, theta 3, all the way to theta n, minus delta 2j, theta 1, theta 3, all the way to theta n. The next one is plus delta 3j, right? Theta 1, theta 2. Now I'm missing theta 3 here, theta n, and so on and so forth, all the way to the n, right? Alternating signs, because the first one, the derivative acts right on front, the second one has to go through theta 1, here it has to go through 2 of them, so it's positive again, and so on and so forth. So product rules will have this alternating sign. And then the main kind of derivative we'll be doing is the derivative towards, say, theta k of exponential of a C number. Let's call the C number A. But this C number will be, in the case we're dealing with fermions, that will show up a lot, right? This A number will be a combination of Grassman numbers. So I'll be interested frequently in derivatives of exponential of a sum of some theta I, eta I, right? Where these are just A numbers combined to make a C number. So essentially what I'm saying is that frequently I'll have exponentials of this general object, but in this case, right, where you only have C number parts of the series here, even for bigger products, right? This is quite easy to do, right? Because you can write this exponential as a series. I won't do it here. I'll give that as an exercise. And you can show that the effect of this derivative will be to bring down this eta, right? And this will be eta k exponential of this sum, theta I, eta I, right? And in the case where you differentiate with eta k, the same thing, then I'll have minus theta k exponential theta I, eta I, which is easy to remember because you can think that you have to go over eta to act on this guy, but in truth you have a series with powers of these, and the truth is to act on eta you have to go through an odd number of generators, and to get to a theta you go through an even number of generators. And of course, even the expansion in series of the exponential itself can be very short if the size of the Grassman algebra is small, the dimensionality of the Grassman algebra is small. But you could show this in general for any finite Grassman algebra, right? That I'll give an exercise, and those that are curious, I have these in my lecture notes at page 133. The next thing we want to define is an integral for Grassman numbers, right? This is not a Riemann sum, right? It's just some linear operator that will have properties similar to those that an integral has for commuting numbers, right? So first of all, we want to define what is this product of integrals, because usually you have more than one variable of integration, so we have to define a sign here. So if I'm doing the integral of some element of this algebra over d theta and d eta, right, this will be defined in this way: d theta, d eta, f theta eta, right? So I'm doing the integral in d eta, the innermost integral first, right? And if I do in the opposite ordering, I have, if I do the integral in d theta first, I will have a minus sign, right? Which is the same as putting these conditions for the symbols, right? D theta, d eta is equal to 0, and I have to do the integral from the innermost one to the outermost one in that order. Right? Also, if I'm integrating one variable, one Grassman variable, and I have a function in another, they will anti-commute by definition. So d theta, d eta also anti-commutes, and that's for any two different Grassman variables. Now, the main property I want, well, I want this to be a linear operator, and I want this integral to have the property to be invariant under shifts, right? If I do a change of variables, which is just a shift in the Grassman variable, I want that to be to not change the integral. So essentially, if I do a change in variables in the integral from theta to theta plus eta, right, that keeps the integral invariant. So d theta of some f of theta that depends only on theta, right, will be equal to d theta of f theta plus eta, where these are two different Grassman variables, right? This again is just an element of the algebra. Let's call that capital F, and it only depends on theta. And this is another element, another supernumber that depends on theta plus eta, right? I can use the general expansion for these two, right? So I can write f of theta as capital A plus B times theta. These are just C numbers, right? A and B. And these needs to be the same as A plus B theta plus eta, right? If that is to be true for any shift eta, right, that means B needs to be 0. Otherwise, this will not be an inequality. So that's the first conclusion, right? But A is even, right? And if this is just equal to some C number A, right, that means that the integral itself, d theta f of theta, is even, or a C number. And that implies that, let's suppose I do the expansion now for f of theta, right? So d theta. Now I do the expansion for this guy. This is just some a1 plus a2 of theta, which can be written as the integral of a1 d theta, because this is a C number, plus d theta a2 of theta, right? Moving a1 to the outside and a2 to the outside goes with being a linear operator, right? But now let's think, this needs to be a C number. The whole sum is a C number. For that to be true, both this part and this part need to be C numbers too. But let's look at this guy, right? If I take the square of this guy, in other words, if I write a1 does not depend on theta, I can write a1 d theta, a1 d eta, just in general, right? Which is the same as d theta, according to the convention I show above. I do this integral first, right? a1 square, right? And again, to the same convention, if I do in the other ordering, which I indicate like that, these two numbers need to be equal, right? Which is, again, if I go back, this is minus d theta a1 squared, right? So what I'm saying is that d theta a1 squared needs to be minus itself, which in this language it means it's either a number, because a numbers square are 0, or it needs to be 0. But it cannot be a number because the sum here needs to be a C number. So this is 0. This guy is 0. Which leaves me only with this part. So what I'm saying is that, and this part needs to be even, right? Needs to be a C number. What I'm saying is that the integral of d theta f theta is in general, right? In general, just this, just a2 times d theta theta, and this part needs to be a C number, because a2 is a C number, so this guy needs it to be a C number too. And I have the freedom to choose this guy, right? Which is usually the convention we'll use for this number, and it's the same most books use. It's just take this guy to be 1. This is a kind of a normalization of my integral, right? And if this guy is 1, that implies that in general, now if I take a variable, an integral of a function of more variables, take, say, d theta of a function that also depends on eta, which is d theta. Let's write the expansion for this guy, a0 plus a1 theta plus a2 eta plus a3 theta eta is equal to a1 plus a3 eta, right? Because this is just 0, right? By what I have shown above. This is 1, right? D theta times theta is 1. Again, this number goes outside the integral. So again, any integral of a constant, right, is 0. So this part is 0. And this one is again d theta of theta, which is 1. And you're left with just eta times a3. Right? So with these definitions, you see that the integral of a function of theta and eta is just this, which is exactly the same as the derivative. Right? If I take that same function and differentiate in theta, you get the same result, which shows that the integration and differentiation in this Grassman algebra amounts to the same, right? The same operation. We will also need equivalent of a Dirac delta, right? for Grassman numbers, and that's easy to see. If I take a generic function g of eta, which can be expanded as s plus b eta, right? This is a generic expansion. What I want is for the integral d eta of delta eta minus rho, which is another Grassman variable, g eta to be g of rho. Right? That's what I want from my Dirac delta, right? And if I write this generically, it will be just a plus b rho, right? And I can do this on both sides, this side and that one, right? On this side, I'll have the eta delta eta minus rho, and I'll expand this guy as s plus b eta. A and b are the same, right? Because there's characterize g, right? And I can expand this as a the eta delta eta minus rho plus b, right? I'm just doing the distributive here, d eta delta eta minus rho eta. And comparing these two, right, this needs to be equal to this one, right? Comparing those two, I see that this guy needs to be 1, because you see, I just get a here, and this guy needs to be rho, because you see, there's only rho here. And that's very easy to get, right? For this guy to be 1, all I have to do is write, let me go a little bit down, I can define actually delta of eta minus rho as eta minus rho. Because if I substitute this here, the integral of this part will be 0, and the integral of d eta eta will be 1, right? I satisfy this condition. In here is the same. If I put this condition, this expression here, right, I'll have the first part will be eta squared, which is 0, and the second one will be just the integral of d eta of minus rho eta. And I need to bring this eta here to write, that absorbs the minus, right? It will be d eta rho, right? Or bring the rho outside, which is the same, also changes the sign. This is 1, and I have rho. So even the Dirac delta is very easy. It's just a subtraction, right? If you substitute that there, you show that you satisfy the condition you wanted. And finally, we want to be careful with change of variables, multiplicative change of variables in Grassman integrals, right? So for instance, think of d theta of theta, which you say it's 1, right? It's the condition we used. And now let's define a eta, which is part of the odd part of the algebra, is a number, right? And now I'm changing it by multiplying a c number, let's call that a, to theta. But I also want now the eta to be 1, right? It needs to be true. So that means that in terms of theta, right? Let's change just this part, right? This is a d eta of theta, right? And I want to satisfy that this is 1 at the same time that this is 1. That means that my d eta needs to be 1 over a d theta, because then if I substitute this here, the a's cancel each other and d theta of theta is equal to 1. So the change of variables, you see, if you compare these two expressions here, you see that's not, it's very unlike what you would expect for an integral, and looks more like a change of variables in differentiation, right? Because this integral is very similar to a differentiation, right? So keep that in mind. It pays to be very careful with change of variables because they are the opposite of what you're used to. Since we know that Dirac spinors are complex valued fields, right, will also be interesting to define complex Grassman numbers, which we'll do in the usual way. You can just take any two generators and combine them like that, right? This is still part of the odd, right? This is a number, right? That now involves a complex and a real, Grassman real and Grassman imaginary parts, right? But we need to define then how is the action of complex conjugation acting on this guy. Suppose these two are complex Grassman numbers, right? And I want to know how these acts here. Right? It doesn't matter for commuting numbers, but for anti-commuting numbers, I have to decide if this is eta star, theta star, or the opposite, right? And there's actually an ambiguity here, but we use this definition, which means then that this is minus theta eta star, right? And remember, you have to be careful with that because that will propagate to the dagger, right? So that's the one instance where you actually invert the order of Grassman numbers without appearing a sign, right? The sign comes already from the complex conjugation. As far as integrals go, we'll do the same we did with the commuting numbers. So we'll write everything, instead of writing in terms of theta 1 and theta 2 here, we'll write it in terms of theta and theta star. But those are now treated as independent variables because I'm treating theta 1 and theta 2 as independent. And I'll be able to write integrals over these two guys, right? So as for the rest, everything works the same way. So the integral will still be given by these two properties, right? The eta is equal to the eta star, which is 1, and if I take one of those stars off, this is 0 because of this property, right? They are independent variables. And of course, same thing as before, I'll be often interested in calculating exponentials of C numbers, which are this composition of two A numbers, right? Two Grassman numbers, which, by the way, is also real if I do the complex conjugation as defined above, right? So this is, again, since this, I'm assuming exponential only depends on eta, then the series for this guy is really short, right? There's no other terms for that series, right? And I can do the integral I'll be doing most of the time pretty easily. So the integral I'll be doing the most, and notice this order is important, as is every other ordering here. But once I know the answer for one ordering, I can do all of them. And this is just this integral. Oops, I forgot the b. B is just a C number, right? And this is easy to do, right? You just B commutes, right? Comes over here. I have to bring this eta to the left to be integrated with this guy. This part is just 0 because there's no eta or eta prime here. In here, I can take the b over here, paying no price, but then I have to bring this guy to the left of eta star, and for that I pay a change of sign, and then d eta is 1, d eta star is 1, and this is just b. Right? Compare these with the case for just complex numbers that are not Grassman numbers. Right? I had before I had I think we did this in some exercise list, but dz star, dz, and there's a different normalization here for these numbers. We have seen this before, of the exponential of minus z prime bz. This was 1 over b, right? So remember, when integrating this Gaussian, right, this is basically the Gaussian integral for Grassman numbers. Instead of getting 1 over b, I get b. And that has a lot to do with the fact that changes of variables for Grassman numbers are more similar to derivatives than integrals, right? And I can also do this other integral, right? Which is also very useful when we will be calculating 2-point correlation functions, right? With the Grassman variables here, say eta star. This one you can do the calculation same way we did before, right? Or you can just take this expression and differentiate in relation to b, right? Just take this, take the minus the derivative in relation to b on both sides. In here I get this, and on the right side I get 1. Which you can do by just integrating too, right? You get this eta star acting here will give me the 1, and eta star multiplied by this part is 0. That's why the b disappear, because you get eta star square and eta square here. So all you have is this. And of course, any higher power of eta star is 0, because these are Grassman numbers. Again, this is very similar to what happened here. But since here I started with 1 over b, if I differentiate, I get, right? I get this integral z star z, and here I have 1 over b squared, right? If I differentiate in relation to minus b, right? So these two expressions, the analogs for Grassman numbers are those two, right? And in this case, I can keep making derivatives in b and getting higher and higher powers of z star z, right? It will be 1 over b cubed and so on and so forth. In here, no, because I started with a power of b, so it's 1 and then 0, as you would expect for Grassman numbers. Right? So that much is clear, and this is the Gaussian integral for these Grassman numbers. Of course, again, the most interesting case for us is not the case where I just have one Grassman number, because we know our fields have many components. I have infinite degrees of freedom, so I need to generalize this for where B is a matrix and these guys are vectors of Grassman numbers. Right, to see how I generalize this, which we did for the Gaussian of commuting numbers, right? But to see how we do that, let's go first for the two component case. So now I'm building a vector out of Grassman numbers of size of dimension 2 for now, eta 1, eta 2, right? And I'll define some eta bar, which for now is not gamma, there's no gamma 0 here, but just to remember that I'm also transposing this guy. So eta bar now just means that, right? It's the dagger of that guy. And we can calculate actually eta bar, eta square, right? This is Okay, eta 1 star eta 1, I'm just making that product, right? Plus eta 2 star eta 2 square, right? And you can see that for Grassman numbers, those products are easier because this first term square is 0, the second term square is 0. All I have is the cross terms, which are 2, right? I have this one, I have this one, and this. Which again, I can just reorganize stuff and rewrite as eta 1 star, eta 1, eta 2 star, eta 2. Just have to keep commuting them till you get this combination, and hopefully you did that even number of times to get this answer. So that means that why I'm doing this, because if I do the exponential now, this exponential there was only one Grassman algebra. But now I want to do with these vectors, and that means that now I have more combinations and I can go farther with the exponential, right? I have this expansion now is 1 minus the product, right, which is just eta 1 star eta 1 plus eta 2 star eta 2. This is just a scalar product of eta 1 or eta 2. But now I have this term square, right, which is, and divided by 2 because of the series of the exponential, will be just eta 1 star, eta 1, eta 2 star, eta 2. And this is all, because now if I try to go any further, I'll have either eta 1 or eta 2 square. And this is 0. Right? And I have to define also this object, right? And by defining, I have a sign ambiguity here, then I have to decide, right? I have to choose an ordering, and of course once I choose that, everything else is determined, right? I'll choose this one, eta 1 star, eta 1, eta 2 star, eta 2, right? So I'll always follow this convention. And that implies now that the exponential, if I do the integral of the exponential, obviously the only term that contributes is this one. Otherwise, I leave one of these integrations free, and that's 0. Right? The only term that contributes to this integral, exponential of minus eta bar eta, is the term where I have all these integration measures and this guy. And now just the decision if this is plus or minus 1, right? I have to bring eta 2 here, that's 3 hops. Then I have to bring this over here, there's 2 extra hops, and then I eliminate it with this one. And then I have to change the order of these 2, which is yet another sign. So in total there are 4 commutations, so plus 1, right? So this is the Gaussian integral for a multidimensional Grassman space. And now if I want to include a matrix here between these 2 guys, all I have to do is a change of variables, right? To show up with the matrix here. So I take eta to m alpha, right? Where m is a matrix, to say eta is 2 by 1, so this is 2 by 2, right? I take eta bar to alpha bar n, right? So m and n are just complex numbers, 2 by 2 matrices of complex numbers, so they are C numbers, right? And then I can rewrite the product. say eta 1, eta 2 as m11 alpha 1, m12 alpha 2, right? This is the first component of eta in terms of alpha, right? Just multiplying that matrix there and taking the first line. And eta 2 is m21 alpha 1 plus m22 alpha 2. And then I have the product. Notice that only the cross terms survive again because it's alpha 2 square and alpha 1 square are 0, right? These alphas are A numbers, right? They are Grassman numbers. So all I get is the cross terms, which are m11, m22, minus, so this is this times this, right? And the other one is this one, right? In which I have alpha 2 times alpha 1. So I'll commute these two. Here I have alpha 1 times alpha 2. So this is the first term. The second term I have the opposite. So I'll commute that to bring this out here. And that's where this minus comes from, 2, 1. Which is the determinant of m. So now remember, this is it. If I'm changing from eta to alpha, I need to find the change of variables for this integration measure, right? Which again is that game. I want to guarantee that this eta 1, eta 2, which is 1 or minus 1, right, is the same as this one. In the way that I'm writing, these guys are both minus 1 because I need to come over here to integrate. Which means now I have to demand, right, that d eta, eta 1, d eta, eta 2 is not the determinant, but 1 over the determinant of m, right? Which is different from what you get from normal integrals, right? I have this minus 1 here. See, at eta 1 and eta 2 are the determinant of these guys, but the integration measure is 1 over the determinant of these guys. Right? I could do the same for the other part, for these two. Now with n, right? And that would mean I would get by the same calculation, but now to the left side, right? The eta 2 star would be the determinant of n minus 1, the alpha 1 star, the alpha 2 star. So finally, if I start from the integral at the beginning, right? I have shown that without the matrix, this is true. And I want to make the rotation. So I have to be careful with the orderings here. I have minus sign to come over here. Right? And then I have d eta 1 star, d eta 2 star, which I'll write as d alpha 1 star, d alpha 2 star over the determinant of n. Right? Then once I brought this guy over here to get that sign, I have d eta 1 times d eta 2. This guy is not in the middle anymore. That I can use this equation to write as d alpha 1, d alpha 2 over the determinant of m exponential, and then I just have to make the change here. I have alpha bar n m alpha. And this now is easy to rewrite as. Again, I fix the ordering here to have my canonical thing, the alpha 1 star, the alpha, reabsorb that sign. These determinants here, the product of determinants is the determinant of the product, so this is just the determinant of n m times, I absorb the sign, the alpha 1 star, the alpha 1, the alpha 2 star, the alpha 2, exponential of this. And then I just take this product of n, m and call A, right? This product of two matrices, this is just a matrix of C numbers, so I don't have to take much care. I just call this A. And then if I look, these must be 1, so I can throw this determinant to the other side and write. And now I just take these to n dimensions, right? I don't have to keep it 2. The alpha bar d n alpha exponential of minus alpha bar a alpha is equal to the determinant of a. Right? Which is, again, very reminiscent of Gaussian integration, right, with C numbers, with the exception that the determinant is in the wrong place. Before, if you did that for C numbers, right, if it was just an integral in Z prime Z, the answer on this side would be 1 over the determinant of A, right, instead of the determinant. So the same thing, before I had B instead of 1 over B, now I have the determinant instead of 1 over the determinant. And this will be very important once we get to Faddeev-Popov ghosts, right? So you see, when you have, you can use this in this direction, right? You can use these kind of equation to write determinants as integrals in Grassman numbers, which we'll see is useful in some very specific situation. It's also easy to show by doing derivatives in components of A. So you take some Aij and differentiate in relation to that. You can show the accompanying expression, which is useful for 2-point correlating functions, which is something like alpha I alpha bar j exponential of alpha bar a alpha, right? And on the right side you get just a minus 1 ij times the determinant of a, right? So this is a consequence of this first integral, right? You can write this second result as a consequence, right? And then naturally we want to generalize here. Here I still have a discrete vector, right? I want to take this to the continuum limit where these become functions, right? So the last definition we'll make in terms of Grassman numbers is some kind of Grassman function. And to do that, that sounds complicated at first, but in order to do that, what you do is very similar to what we did in the canonical operator approach. So if I want to define a field psi of x, which is behaves like a anti-commuting, a Grassman number, part of the odd part of the algebra, all I have to do is define these as a sum over the Grassman generators, let's call this psi I, times functions which carry all the rest of the indexes. This is very similar to what I did when I wrote psi as some kind of a of p, right, which carry the operator character of psi times a v of p or a u of p, right? And then the spin index, right? I kept all the Dirac indexes here. I kept the function, I mean the dependence in P as a function here, but I made this coefficient take care of the anti-commutation relations. Here I'm doing the same, right? So this is a number, because this guy is a number, and then I just have to decide on how many of those guys I'll need. And the continuous character, I mean the function, is here. This is a C number, a commuting number, right? And that's how you build Grassman functions. Then it's very easy to see that if I put that here, I can get continuum path integrals, right? I can do path integration, deep psi exponential minus psi bar a psi as the determinant of a, right? But now what is, I'm changing over all the shapes these functions can get, right? At the same time, I kept this I is not the index I'm making continuum. This is just an index over the Grassman algebra, right? Which is finite, right? I can keep my Grassman algebra finite and have functions which are just complex numbers here, right? And write Grassman, I mean path integrals for Grassman numbers, which will look like that. Again, before I had 1 over the determinant of this operator, right? There's an operator here, and now it's just the determinant of the operator. All right, then. Now that we have this arsenal of Grassman number properties, right? Let's do the same we did for the scalar fields and ditch the space coordinates. Let's keep just time and go back to quantum mechanics and do the Fermionic harmonic oscillator, because then after we know the results for just one parameter, right? Let's say field theory in 0 space dimensions, then we can just generalize to the 4-dimensional case and go to Minkowski space. Right? The Fermionic harmonic oscillator is just the oscillator that has this Hamiltonian, which is recognized as a very similar one to the bosonic one, right? B dagger, B. Just using B for in order to differentiate from the A, which is for the bosonic harmonic oscillator. There's no A dagger here, it's just B dagger B, right? Minus half. And these B's and B daggers satisfy these relations. So this is anti-commuting relation between B dagger and B. This is similar to what we get in the canonical formalism. Now I want to use this and make a path integral to see how the path integral to the Fermionic harmonic oscillator looks like, right? Again, the proper way to do that is to use coherent states, right, which are characterized by some number beta. And you remember, these are just the exponential of the creation operators acting on the vacuum of the Fock space. But now, since this guy is anti-commuting, I need to make consistently beta be anti-commuting too. So beta is a C number. This is part of the odd part of the algebra, right? This is a Grassman number, and this is B dagger. Of course, there's I could use the opposite definition, and this is a convention again. Right? If I use the expansion for the exponential in terms of these guys, it's just 1 plus B dagger beta acting on 0. I don't have any extra powers because beta square will be 0, right? And these I can write as 1 minus beta B dagger acting on 0. On the other side, if I look on the action of B acting on beta, right? This will be B acting on this, which is just B plus, let's use this expression, beta B dagger, right? it was B dagger B, B dagger beta, but then beta goes through two guys, the sign keeps the same, right? Acting on 0. I can write this using the commuting relation as 1 minus B dagger B, which then this is an annihilation operator acting on 0. So this is just beta times 0, which I can, just for comparison with that one, write as beta 1 minus beta, because beta square is 0. So I'm just adding 0 here. Beta 0, right? Which I recognize from this expression as beta, right? So I'm showing that this is beta, which is what we expected, right? So these are eigenvectors of B with eigenvalues beta. And here, if you didn't buy my excuse to make beta a Grassman number, now it's pretty clear, because when we go from canonical quantization to path integral, I will exchange operators that depend on B by functions that depend on beta. And if beta is not a Grassman number, I lose the anti-commuting properties, right? For sure, this is what I'll be putting in the Hamiltonian to make it, I'll exchange operators by their eigenvalues, right? So the eigenvalue needs to be a Grassman number if I am to keep the anti-commuting character of these fields. So this is where the Grassman number comes from, right? It's the eigenvalue of this anti-commuting operator, right? Then I have completeness relation, which is in this case is easier to prove, but it's very similar to the one we got in the complex case, right? Just go back to the bosonic case and take a look, and you see. So this is the completeness relation for these coherent states. And I want to use that to build a path integral. So let me write the Hamiltonian. Now I'm putting sources in. Same thing I did for the harmonic oscillator. So I look at the forced harmonic oscillator, B dagger B minus B dagger eta. This is the source. Right? It's a Grassman number too, because remember, I need the product of all those guys in there to be a C number. So when I replace these guys by their eigenvalues, they will be A number. So I need to multiply by another A number to get a C number. The Hamiltonian needs to be a commuting number. So these sources are Grassman variables again. And this is exactly what I said before, is the dagger. There's no gamma 0 here. It's just the complex, the dagger of eta, right? And then I want to use these completeness relations in a transition of this sort, right? So T prime. So I'm starting in a time t with eigenvalue beta, and I'm ending at time t prime with eigenvalue b star. Remember, I cannot fix beta and b star at both ends of both as initial and final conditions, because their operators do not commute. So I have to choose to fix beta at the start, and that means b star as the start is not fixed, and I'm fixing b star at the end, but beta is not fixed, right? And this is this object, which I'll turn into a path integral. Right? I'm trying to focus only on the differences here. I won't do everything again. whenever it's the same to use commuting or anti-commuting numbers, I'll just keep some steps. Right? So now I in the middle here, I insert a bunch of these identities for every value of beta. So I slice time into many small slices and insert identities like that, right? Until the point where I can just turn this into a continuum, right? And write this expression, right? This is the same I did before. In each of these slices, the Hamiltonian will appear, right? Because I can take this time evolution between states in the middle will be a exponential of the Hamiltonian. The Hamiltonian then acts on states that are infinitely close in time to the point where I'm acting to with the Hamiltonian. So I just exchange these operators by their eigenvalues and write everything in terms of functions now. Right? That has no difference with the commuting case. It's just the same thing, so I won't do it again. T to T prime, d tau, and here I have a Hamiltonian written in terms of eigenvalues. So B star that depends on tau, beta tau minus the Hamiltonian beta star, right? Just the eigenvalues, time, and I have that the integral in time is just including this part. This is outside the time integral now. It's just that term that depends on the edges. If you don't remember any of this, go back to the forced harmonic oscillator and look the steps we took there. The only difference is that here you have to be careful with the ordering. This is actually b dot, right? There's a time derivative here. You have to be careful with the ordering, and when we need to reorder something, you have to change the signs accordingly. That's all, right? If I take the classical solution, right? If I take and look for the classical solution for that, it's given by the Hamilton equations, which are for B star of tau is this one, B star of tau plus I eta bar of tau equal to 0. In this case, eta bar is really different from eta, right? Because we're dealing with complex fields here, so the sources are also the complex conjugate of each other, right? And beta dot of tau will be I omega beta of tau minus, in this case, minus I eta tau equals 0, right? With the boundary conditions, as I said at the start, I'm fixing beta at t, and I'm fixing beta star at t prime, right? Again, go back to the forced harmonic oscillators, the same thing we did there. Now we want to generalize these results we got from the fermionic oscillator to a fermionic field theory, right? Which we'll do next video. For now, let me just put these in a more familiar notation, just to make easier our task next time. So now I'll just exchange, for now, beta by psi, right? And this beta by psi bar, right? But these are still fields in 0 plus 1 dimensions, right? So 0 dimensional space, there's just time, right? In that notation, we can rewrite our z of eta prime, eta bar, as path integral in psi bar, path integral in psi, exponential of I dt of minus I del t psi bar, this time derivative is this b dot here, psi minus omega psi bar psi plus psi bar eta plus eta bar psi, and I close the exponential here. Right? I want to write this as a psi bar operator psi, right? So I have to do integration by parts here, which is fine because remember this expression I'm already calculating for z in the limit where the initial and final conditions are that the betas are 0 and now my psi's are 0 at those extreme points. So I can rewrite this term right here as I psi bar del t psi, right? And then my z becomes just del psi bar del psi of the exponential of the integral dt of minus psi bar df minus 1 psi plus the integral in dt of psi bar eta plus eta bar psi, and that's where the exponential ends. There's an I here that was missing, right? And here there's no I because I included this I in the definition of df minus 1, which now is defined as minus I del t minus omega. So I hope all the signs and powers of I are okay, right? And then I have defined this operator, right? You see, everything is very similar to the scalar case, right? In the scalar case, at this point, we would have just something like that, right? Delta phi, right? Or delta minus 1 was the operator, the Klein-Gordon, right? Operator, right? And here I had just j phi, right? Phi delta phi and j phi. And this is the same, right? This is the part with the fields and the operator, the Gaussian part. And this is the sources, right? The external sources that I have here. In this case, since I have two independent fields, I need two independent sources. And then I can rewrite this as we have done for the harmonic oscillator in a better way, right? The equivalent of this. Right? We can just rewrite z eta bar as the z in the absence of sources, right? Very similar to what I have here, times the exponential of minus ds d tau eta bar s df s tau eta tau, right? And just by comparison, you see the f needs to be the inversion, the inverse of this one, right? And you can easily show that you can apply this to the following function and find that it is the inverse. So I will just write the expression for this propagator. Remember that we're still in zero spatial dimensions, right? We have just time and energy here. Del t minus omega minus 1, right? It's the inverse of that, which is I dE over 2 pi e minus omega plus I epsilon exponential of minus I E s minus tau, which is actually easy to integrate and gives you theta of s minus tau exponential of minus I omega s minus tau, right? Let me put a box around this. So next time we'll go to the Euclidean space and bring back the space dimensions, right? We'll go to a field theory in 4 dimensions. But for now, there's a few things we can notice here. The first thing, and that in comparison with the bosonic case, the first thing is that I have only E here and not E square like I had in the bosonic case. That means there's only one pole in here, right? And that means that since I have only a pole, let me write this explicitly, right? First thing to notice is that the pole is just E equal to omega minus I epsilon. There's no, before we had 2 poles, now we have just one. That implies that when I'm doing this integral from get to this expression to this one, right? I have to decide, right? I have to do this by residues. I have to go to the complex plane, right? And I have to worry about the sign of the imaginary part of the energy, right? It just happens that if I do the integral for the imaginary of E bigger than 0, right? A close over the upper hemisphere, right? This, I won't get the pole, right? I'll go, the pole is below, is at negative imaginary values, right? So if I close my integral on the top, I miss the pole and the integral is 0. And I'm forced to do that if s is smaller than tau, right? So if s is smaller than tau, this is positive. This needs to be bigger than 0 so that the integral over the circle is 0, and this is negative actually, right? So the integral is 0. So this integral is only different from 0 if s is bigger than tau, and that's why I have this half-side function here, right? This integral is only different from 0 on s bigger than tau, right? And in this case, then I have to close on the bottom, right? And I get the pole and I get these, and then this result is true, right? E is just equal to omega, right? That's the second thing to notice. So that's already different from the bosonic case, and it's important to notice that we don't have any more this symmetry between s and tau, right? Before, I didn't have to worry too much about the ordering of the arguments in this propagator. Now I have to be careful about that. That will have a bunch of implications. So that's what I had to say for today. Again, next time we'll go into 4 dimensions with this thing. See you then.